and I take value y2 minus ay1. So
y2 is found from
here is still, so I replace this as with some value a. I replace this with y2 minus ay1.
And could you write it not involving y2 and y1 so that William doesn't get upset?
Yes, yes. I will do it in a moment. So if you
I understand what you mean. You actually write down mu1 x1 plus y plus mu2.
Yeah, so this actually will give you, okay, y2 is this expression, y1 is actually a star. So
they cancel.
Yeah, they cancel, and you see that it's actually equal to y2.
Right.
It's the same y2.
The same y2, yes. Okay.
And since I didn't change x star, that y1 is unchanged. So for every a, you get new set of parameters.
Yes.
So, and here you also have say some words that for any this set degenerate parameters, you can avoid it.
So you're saying this example violates the uniqueness?
Yes, because it's not unique. You
Because
pick something, and then you can take new one.
Because, right. Okay. Okay.
Does this answer your question?
I think the idea is that you're saying for any choice of y1 and y2, but really what you mean is you're given y1 and y2. That's part of the original. That's observed.
No.
And
what he's saying is that y1 and y2 as functions of the parameters is given like that. So think of mu1 and mu2 and x star as variables. Okay? Now, you can pick a particular x star 0 and the mu1 0 and the mu2 0. That determines y1 and y2 already.
Yes, that's correct.
And then if you put it in there by varying a there in that formula, you actually get a different mu1 and a different mu2 and a different x2. So they're not uniquely determined by the y1 and y2.
Right. Yeah.
Is that correct?
Yes. This is how the definition should be checked. Yes.
Right.
Okay.
It violates uniqueness.
Yes.
Almost like it's amazing that it violates uniqueness in a linear situation.
Yeah. So somehow underlying reason for this violation is that our system has some conserved quantities. So because we have in language differential algebra, you have new constants. And like from differential Galois theory, you know that new constants is always kind of headache, and this is where this headache appears in this context, actually quite unexpectedly. So this is the assumption might violate in the presence of conservation laws in the system.
So actually,
Some.
So I just want to understand it.
Okay. Yeah, please.
So actually, the reason why it's not unique is because you have two equations. Say y1 and y2 is given. I mean, observe. But you have three unknowns. But that's why you can't have a unique solution. You don't have enough equation, actually.
Yes, I don't have. Okay, yeah, this is another way to check that this is actually non-identifiable.
So because of the uniqueness condition, you must have as many equations on y as there are parameters. At least. Okay.
No, I mean, in principle, you have infinitely many equations in y because you can differentiate this until you are completely tired. I mean,
No. I don't mean there are unique system. I mean, in every system where you can use the y's to determine the parameters, they have to be as many. I mean, it has to be. Well, how do we express the fact that the system has only defined a unique solution if they're not linear? But that's what it is. But you said it's linear anyway, eventually. So in terms of linear, then you just simply have to say that the determinant is not zero.
okay. So you don't have any equation.
Yeah, but if it's non-linear, I don't know how you express the fact that a non-linear system has a unique solution.
You can check it.
Which means that the variety defined I mean, in the parameter space, the variety that defines parameter space is one single point.
Yes, it happens.
So what's the condition on that?
It's
Not only
a
is
hard
dimension
problem.
zero, is dimension zero, but it's also far more than that.
It's a hard computation problem to check that. I will speak about it.
Okay, good.
I hope. So, okay, so in what situation are we right now? We don't have a general algorithm that works with guarantee and with reasonable speed for global identifiability.
What do you mean we don't have?
I and my co-authors. Okay, so like a couple of months ago, we didn't have. Yes, sure.
Now you have.
Yeah, thank you. So yeah, we didn't have. So and now I would like to present how do we approach this problem. So I will use still.
You explain it roughly, but
Yes, I will roughly, because I will omit some details. I will omit all inputs. They don't really make situation much more complicated, and I will show you how it works on some example. This one actually. So this is example that we already have seen: exponential and shift, and you're going to take the equation for y and start differentiating it. And each time, like differentiate one time, mu2 disappears, and you have x dot. And you say, I have an equation for x dot that expresses x dot in terms of mu's and x. So I don't allow x dot to appear in some sense. I immediately replace it. Then I differentiate one more time, again x dot appears, I again replace it. So after I do this, I will have infinitely many equations of the form certain derivative of y is equal to a polynomial in mu1, mu2x. So geometrically, this is a map from C3 to C to the infinity. Okay, so I map every triple mu1, mu2x to the whole bunch of derivatives of y. In general, you have S parameters and you have several outputs. So in the same way, you can obtain a map from C to the S from a parameter space to certain infinite dimensional affine space. So this is almost algebraic context. So you have polynomial maps. Polynomial maps are algebraic objects. So they're a bit infinite, but we'll deal with it later. So what I want to say that we want to reformulate to give equivalent definition in terms of this map without involving analytic functions in differential equations and so on. So this is equivalent definition in some sense. Or it's a way to check the global identifiability using this geometric picture. So the parameter is globally identifiable if all elements of this set have the same ith component. What is this set?
just slow down and let people read it.
So phi is my map from parameters to y's, and this set, inverse phi of p, is actually the set of parameters that will generate the same y's, roughly speaking. So, and what I say that for every such parameters,
Like those.
yes, like those. So I have this different choices of mu1 and mu2 will be actually this inverse, this pre-image. So, and I say that parameter is globally identifiable if for every element in this pre-image I have the same value of this parameter. So I can. Oh, pardon?
We have this room for a class.
At 45?
Yeah.
Okay, so
Yeah, it's not a confusion we have it.
Yeah.
I'm not trying to.
It's fine.
Yeah. Okay. I will finish by
We
that.
can always continue a little bit in the afternoon if we have time.
Yeah, okay. So so this is the reformulation in this geometric language of our initial definition. and this is equivalent. The problem is that we have infinite dimensional spaces. We cannot work with them constructively. Okay, so we would like somehow to make the situation finite dimensional. So how can we do that? If we have such map to infinite dimensional space, we can truncate it. We can throw away components that correspond to too high derivatives of y.
What do you mean we can truncate it?
Yeah, we can construct, starting from this map and taking some tuple of non-negative integers, we can construct a polynomial map within finite dimensional spaces from our initial map, just ignoring some coordinates of the image.
I don't understand the quantifiers here. How is h quantified?
For every phi and every h,
So you don't find.
no, I don't find. For every h, it's really h. For every h, I can construct such a map. And this is kind of finite reduction of my big map. And what I want to find h such that this reduction will not lose any important information, so that I can use this h instead of the whole infinity. And this is actually next theorem. So I find h, any maximal h, such that this truncation is surjective, and I do one more step. And then make one more step, and then this truncation carries enough information to make a decision about identifiability. So I can replace phi in the theorem in the previous slide by this one.
And there is an algorithm to calculate this.
There's an algorithm. I will say about the algorithm. So, but just for now, if I
5 minutes.
okay, so yeah, and there's an algorithm. So first I can find such h. It's not hard. It's also some Jacobian business. Then I pick a random point parameter space and compute the pre-image. So there are two things: random point and computation of pre-image. For computation of pre-image, you can do any polynomial algebra you want. Okay, stop. Close the door. Wait, for the computing of pre-image, you can use any polynomial computation technique. Currently, we use Gleb databases. This random point, we did some analysis, so you can guarantee any probability of success that you want, less than 1. So, based on the input data of degrees and orders and number of variables, you can compute some way of doing this random choice that this result will be guaranteed to be correct with probability that you want, that you set.
So it's not just speculation that will take something random.
Yeah, it's not like high probability or no, just say me you want 99%, I give you 99%. This is a rigorous thing. And okay, just to finish, this is an example, some chemical reaction, and this is okay, it's reasonably large. And if you set the probability 99.9%, the algorithm says that everything is globally identifiable in 1.5 minutes. So, and this is, you cannot deal with this with Rosenfeld governor.
Wow.
It just will not finish. So, and yeah, this is I think the end of the talk. Thank you for attention and for
Questions? More questions?
Could you go back to like 2 previous slides?
this one.
Oh, sorry, one more previous.
One please.
So I'm a little confused. Aren't you still sort of computing an input-output equation in the sense that you're taking derivatives and then, plugging information back in? Isn't that?
I don't eliminate x.
But in this example, x was y minus mu2.
But you don't know me too.
Right, but I'm saying that.
If you want, you can replace x with y minus mu2 here and get input-output equation. But I don't do that. I do different thing.
Okay, but
I don't eliminate x's. I keep them all the way.
okay.
So, but of course, in any method you will differentiate some at some point, and there's subtle things
Okay.
Which order do you do that?
Do you actually rule out any singularities because you talk about global identifiability? Is that local?
Pardon? Is your question, does global identifiability implies local? Or-
Yeah, no.
Okay.
I'm saying that in your calculations, because you are aiming at global identifiability, do you ever encounter any singularities?
I mean, okay. Maps that we construct can have singularities.
Okay, then how do you handle it?
In what sense? I mean, I compute the pre-image. I don't need to think about singularities if I compute pre-image of the point. Okay, let me put other way. Do you ask what will I do if my pre-image will touch the singularity?
For example,
I avoid this with the high probability making